Good afternoon, everybody. I hope you guys are doing all right. I hope that you have I guess any damage that was done by last week's weather you that's been fixed. Um, so what we are going to do in the lab is we're going to do the lab that we were planning on doing, and that is the Bradford assay. I made a video of the Bradford assay, and I have data that I will provide y'all with so that you can go ahead and work on putting together a standard curve. Um, the the video that I made is roughly 30 minutes, and that video was originally going to be used by your IAs to basically direct the lab meeting when we were going to do it remotely, but we are not going to do that at this point in time. We're going to go to the lab. And so that video is about 30 minutes long, and that video included prepping some of the solutions. So when you guys get to lab, you will have a fresh bovine serum albumin stock. You will have a fresh Bradford reagent stock, and you'll have a visible light spectrophotometer or spectrometer. I can never remember the difference between a spectrophotometer and a spectrometer. I remember, though, not too long ago, I was very defiant, and when someone said spectrometer, I was like, spectrophotometer? I think that it has to do with the wavelengths. Could, maybe, I don't know. At any rate, the data that I put together for that, let me see if, oh yeah, I do. I have it in an Excel spreadsheet, and I'm going to go ahead and share screen. I think I'm going to devise some sort of coded language so I don't have to say share my screen anymore, because I feel like everyone's heard those words in that sequence way too often. So I'm going to say, I'm going to now floop-de-doo, and then everyone will know when Dr. Gray says floop-de-doo, that means he's going to share his screen. But anyway, this is the data that I'm going to email y'all, which, let me just tell you that if I were, some of y'all are the very good students in this world, and what you're doing is you're seeing that data and you're like, oh, sweet, he's going to give us this data later, but I'm just going to copy it down now. And for those of you who are like that, awesome. A younger Joel Gray would have been like, it's right there. I could do this assignment while he's talking about it, but I don't really want to stress myself out too much. So I'll just wait till the file is sent to me. And then 15 minutes before the due date, that's when I'll focus on it. So as you can see, I have a very complicated system of, well, what the dilutions consist of and the absorbances. So in column A, what I have is a description of what is in that cuvette. So if you look at at cell 2A, you'll see that I've typed in 900 BR, 50 H2O, and 50 Pro. Okay, so that stands for 900 microliters of the Bradford reagent, 50 microliters of water, and then 50 microliters of my non-diluted protein sample. What I did was I mixed those three components together, and I measured the absorbance at 595 nanometers. 595. And the absorbance ended up being approximately 0.542. Okay, so what that tells me is kind of a high watermark of sorts. Whenever you have as much protein as you can possibly have in there, you get an absorbance of 0.542. Okay, so then my next sample, if you look at cell 3A, that has the exact same composition, but I'll bring your attention over to C3 or 3C, whichever way you look at that. And that tells me this is the first dilution. Okay, so the way that I made my dilutions, dilution 1 equals 50 microliters of protein protein, how about spell it right, plus 50 microliters of DH2O. So if your stock, let's go ahead, one of the things that I always like to think about is, well, how much total protein is in there? So let's say that our undiluted stock was 10 micrograms per microliter. So I'm going to move this over here. 10 micrograms per microliter was the concentration. In sample number 2, does anyone know approximately, well, how much protein is in there? And let's go ahead and I'm going to type in protein amount. So what we did was we got 50 microliters, and that sample's concentration was approximately 10 micrograms per microliter. So the total protein in there was, would everyone agree with 500 micrograms? Okay. So then my next sample, C3, that was the exact same composition, but my protein sample was a dilution. And so that dilution, I need to know what the composition of that dilution was. That dilution was made by adding 50 microliters of my protein and 50 microliters of DH2O. So a total of 100 microliters. I took 50 microliters of that and added that to make my second sample. So what would be my total protein amount in this sample? 250 micrograms. Does that make sense?
Yes, sir.
Okay, fantastic. So I continued doing this by taking, for dilution number 2, I said 50 microliters of, I'm going to call this dilution 1, plus 50 microliters of DH2O. So what I'm doing effectively is cutting my protein amount in half every successive time. So I'm making serial dilutions, which I don't know if anyone ever listened to the podcast Serial. I was about that many days old whenever I realized series and serial and the connection between those two words. And then I was like, oh, I don't know if I was dating my wife at the time, and I was like, I think that if I say this, she'll think I'm really dumb. So I said it. And she was like, yeah. At any rate, so the protein amount here is 125 micrograms. So every subsequent dilution 3 was 50 microliters of dilution 2 plus 50 microliters of DH2O. So one of the things that I think is a little bit confusing is, what was the total volume of each of these dilutions? Well, the initial total volume was 100 microliters, because half of it went into my sample to measure the absorbance, and then the other half went into the subsequent dilution. So I kept reducing the amount of my protein over all of these different trials, and here are the absorbances that I got. I got 0.542, 0.256, 0.135, 0.063, 0.016, negative 0.001, 0.019, and so on. Now, this is something that is important to appreciate about this. These negative numbers, what does that mean? Do they mean anything? What sometimes people have a tendency to do is they'll look at it and they'll be like, oh, it's a negative number. I don't know what happened, but it's probably the instrument malfunctioning. So I'm going to take that negative number and make it a positive. That's the optimists of the group. In this case, we don't want that optimism. In this case, you record that number as it is, because that result is that result. And what I mean by that is the instrument itself is not smart. It doesn't introduce its opinion. Instead, it just says, well, relative to everything else, it's negative 0.001. So what does that tell you about the protein amount in there? It tells you that it's effectively nothing. Now, do you know that there is actually some protein in there? Yes, you do. But more than anything else, your important takeaway is, well, these samples right here, well, those are probably so dilute that the instrument that I'm using cannot or is not sensitive enough to detect them. So whenever you see negative numbers like that, I don't want you to be like, oh, I did something wrong. Oh, something went wrong. No, take them for what they're worth, or take them at face value and say, okay, well, the protein amount there is so low that I can't even recognize it, or I can't even detect it. Now, when you look at, let's see, this is a total of 10 data points. You might look at that and say, well, half of those data points aren't any good. This is the time whenever I want the optimist to reemerge and say, aha, but half of them are good. So I've got something that I can build a graph based on. And so what we can do is we can look at and compare, and basically we can make two different graphs. And I'm going to show you how to make those different graphs. So the very first data point that we see in this row number 2, in that sample, the concentration of my protein was 10 micrograms per microliter. The amount of total protein in that sample was 500 micrograms. In row number 3, the total amount of protein was 250 micrograms. The concentration of protein was 5 micrograms per microliter. I'm just going to go ahead and, can everyone kind of predict my trend here? Okay, so we got 2.5 micrograms per microliter, 1.25 micrograms per microliter, and then that would be 1.25, 0.625 micrograms per microliter. And actually, because I don't want to get my calculator out, that's where I'm going to go ahead and stop. 125, 62.5 micrograms. Oh, but darn, I can't really stop completely. That would be 31.25 micrograms per microliter. Or sorry, micrograms. Okay. How does everyone feel about the numbers that I've generated here? Okay. So what I want to show y'all is that we can generate two different graphs. Now, one of those graphs is going to be our absorbance. And this is where, oh, rats. Okay, I'm going to move column C over here. There we go. Okay. One of these graphs is concentration versus A595. I'll go to scatter plot. Oh, that's a fun one. That's dumb looking. Let's see. How about this one? Yeah, that's a good graph there, Joel. Good job. Good job. How about this? Doesn't like words. That's what make. Oh, what in the world is that? 10 micro. What? This is whenever somebody usually chimes in. Oh, wait, I see. I think my units are the problem. Somebody usually chimes in and they're like, oh, do you not know how to use Excel? And then I say, no, I don't. I did not take business computer, what was it? BCS, I think is what they called it. Mrs. What was her name? Barrett. Mrs. Barrett taught that class. And she always looked mad at me, so I didn't take her class. She was one of those teachers who was like, your brother was in my class, and I never knew how to take that. Generally, it wasn't a good thing. And then I'd later find out they loved my brother, and they never liked me from the get-go. So that's that. Okay, I deleted that one because what I want is I want to flip my axes. So I'm just going to do this, cut, and paste. Okay, so here's all my data. Scatter plot. On my y-axis, what I want to see is absorbance. And I know that my absorbance range is from 0.016 all the way up to 0.542. My x-axis tells me my concentration of my sample. And that ranges from 0.625 all the way up to 10. Now, this is a total flex because my data looks pretty awesome. and I always feel hip whenever I say flex. But I want to go ahead and show the chart. I didn't ask for that email. So what I see here is my graph that gives me my equation for my line, y equals 0.0551x minus 0.0113, and an r squared value of almost 1. So that tells me that my data is pretty darn good. It's very linear. Now, with all of that said, when you look at this data, if you get so the value of this is now what you could do is get an unknown sample, measure the absorbance of it, so long as the composition of what's in the cuvette is the exact same. 900 microliters of the Bradford reagent, 50 microliters of water, and 50 microliters of a protein sample. Does that all make sense? So if you use that exact same composition, then you can say an absorbance of, 0.447. Well, I could plug that into my equation and say 0.447 lands approximately here. So my concentration of that unknown sample is approximately 8.5 micrograms per microliter. Does that make sense? Okay. Now, so that's with the data that I generated there, whenever I'm looking at concentration versus amount. Now, with all of that to say, you can also generate a graph that shows you, I'm going to copy this, copy my absorbance, and I'm going to copy my protein amount. Who's the fool who wrote micrograms? Oh, 5. Okay. So now I'm going to generate a graph, and it's probably going to look pretty much the exact same. My axes are a little bit different. My trend line, equation on my chart, my r squared value. Okay. It largely looks the same. Now, these graphs are different though, because of the fact that, well, you're comparing on the graph that is in the foreground. I'm looking at absorbance versus amount of protein compared to absorbance versus concentration. Now, the reason that this is important to distinguish between these is that, let's say that your protein sample, your unknown protein sample, you only have 20 microliters of it. Well, if you only have 20 microliters of it, you're not going to be able to make that mixture of 900 microliters of the Bradford, 50 of the water, and then 50 of the protein sample. Does that make sense? So in that case, what would you do? Well, you'd say, I can use 10 microliters of it to determine the concentration. So then I'll have to offset that volume difference by doing 900 of the Bradford, more water, and then 10 microliters of my protein. Does that make sense? So then your composition of that mixture is different. And as a result, what you would be solving for here is you would be solving for amount of protein. And as soon as you have amount of protein, you could say, well, my Y value is, let's say it's right here. My Y value is 0.375. Therefore, my X value is 325 micrograms. And you'd say 325 micrograms of total protein in a fraction of only 10 microliters of that sample. Does that make sense? So think about this and think about these two different graphs as they're both worthwhile, but you kind of have to be a little bit dynamic based on what your sample has, or what you have of your sample. Because if you have a very limited amount of your protein sample, well, then using 50 microliters of it might be problematic. Does that make sense? Okay. So I'm going to give you all this data, and what I want y'all to do is when you go to lab, basically cook up something similar to this. This is your practical final exam. Spoiler alert there. Now, with that said, whenever I say that, historically people say, "What? You mean that if I'm off by whatever percentage, then I get a 0 on the practical final?" No, that's not what I said. And that's usually someone who's very impatient. And they're like, "I need this information immediately." And I say, "Well, I'm going to talk to y'all." So your practical final exam, what you will do is you will present all of your data. You will have the option to remove several data points. And you'll also have the opportunity to develop error bars. So what I want you to do whenever it comes to the final exam, you'll have like an hour and a half, and you'll have a specific volume of a known sample and a volume of the unknown sample. And what I want you to do is try to get as many data points as you can to make that standard curve. And you'll make one submission that shows all of your data with an approximation as to what the concentration of your sample is. You will also say, well, here's 2 data points that were seemingly statistical outliers. So I'm going to remove those. Now the R-squared value has gone from 0.75 to 0.954 or something like that. You will submit that graph and a prediction of your unknown's concentration based on that graph as well. So it's almost like you're making 2 submissions of what you believe your concentration of your unknown to be. And what I'm going to do is I will look at the one that is closer of the 2. I will be subjective in that, and I'll say, okay, well, this one's closer, so I'm going to grade based on that one. Now, that's the instance where I'll be subjective. And so this is a technique that I want you guys to be able to practice as much as you can. And what I would recommend is when you get to lab next week, if you're working with another person, make sure that you get your own time to try it. In addition to that, think about what is the best practice for me to move through this briskly. An hour and a half, I would argue, is plenty of time to complete this. I would argue that an hour and a half is enough time to probably do it 2 times. And you'll have the resources whenever the final exam rolls around. You'll have the resources to do it multiple times so that then you can kind of fine tune your data even more. And in addition to just practicing it more and more, you'll then get a little bit of familiarity and comfort with, well, I put 50 microliters of my undiluted sample and I got an absorbance of 1.9. I've never gotten an absorbance of 1.9. Okay, I'm going to try that one again. Then I'm going to do one simple dilution and see what my absorbance is, so that you have some sort of comfort in additional data that you generate, so that you can kind of affirm that. So when you leave and then you go on to make your graphs, you're not leaving with data where you're like, I have no clue what I'm going to do with this. I hope that this works. Instead, you'll leave with all this data looks pretty good. I'm guessing my unknown has a concentration of this. All right. Also, this is a little bit of a secret info. The unknowns, and you might hear this and be like, this guy's lazy. Not practical, pragmatic. The unknowns are always dilutions. So the most concentrated sample, I'm going to dilute it less than that. So in the event that you get an unknown absorbance that's 6 times your undiluted sample, you might have mixed your samples up. So, and the last thing that I'm going to say before I open the field for questions is you always want to be using your known sample to generate your standard curve. Using an unknown sample to generate a standard curve is difficult, because then you look at it and you're like, I have no idea what any of this means, because you have no idea. Okay, that's all that I have to say. Does anyone have any questions?
I have a question. For the final, would do we need to make two standard curves with concentration and absorbance, and then the other one with protein amount, or can we just make the concentration?
And that is a fantastic question. You do the one that you're most comfortable with.
Okay.
And I will say, I will qualify that you'll have, I'm not going to throw a curveball and say, oh, you only have 9 microliters of the unknown.
Yeah.
You'll have plenty. So you can do either one.
Okay. Would you say concentration is more? I would think concentration is more beneficial because you can directly like see.
Okay. This takes a lot for me to say this because I'm a very stubborn person. Um, it's better.
Okay.
It takes a lot because I always like to do the absorbance versus amount because then, there's a stupid stubbornness of me that's like, no, this is the right thing to do. The concentration versus absorbance is a lot better and faster.
Okay. Thank you.
Sure thing.
Dr. Gray, I had a question.
Yes.
So I was under the impression that we were supposed to watch the video and like do this virtually. So I kind of like already started it last week.
Fantastic.
And the video that was posted like walked us through a function in order to change those negative numbers that you got like for 6 through 10. And I got a different graph than you just got. So I was wondering like if that was wrong or not.
It walked the video that I made.
It was I don't know, maybe it was my IA, but it was posted like under like he sent us an email and it was like posted under the data.
Yeah, and we got all. I'm in the same lab as Or, and we got all the data last week. So I've had it all this whole week.
And
Okay.
like my R squared was like 0.6. So when you got 0.9, I was kind of worried.
Yeah, you're pretty impressed. You're like, Dr. Gray is good at R squared values.
Yeah.
Well, I think your R squared value can kind of simply be attributed to I omitted those data points. I did not include them.
I tried because I sent it to my IA and he said it looked good and to try omitting those data points, and then I did, and it barely raised it to like 0.7, and he said it was fine. But again, when you got the 0.9, I was a little confused.
Well,
I did it with all the numbers and I got 0.9928. So, but I didn't get rid of the negative numbers. I have all the negative numbers in mine.
Did you? I don't
I don't
know.
know.
Well, so I think that the best practice is to omit those data points because it's kind of like a significant figure whenever you put something on a digital balance. You don't add extra decimal points because it's kind of outside the range of that instrument's kind of abilities of sorts. So it's not sensitive enough to give you a concentration or an amount there. I'm not sure what video you're talking about, though, with respect to what your IA posted. So I'll have to get in contact with Armand and see what that is. Now, having already done those plots, then I would argue that you're in fantastic shape for going into lab on Monday. It would be. But yeah, I'm sorry I can't really answer that though.
Okay, no worries. I guess I'll just wait till lab.
Okay.
Thank you though.
Sure thing. Thank you. Anything else? All right. Well, I'm going to go ahead and stop the recording, and I'm also going to wish you guys a great afternoon. I want to stop the recording after that, so everyone's like, wow, that guy's really nice.